All right. So we're going to look at chapter 9 problems now. We're going to do these ones here, starting with number 50. Okay. So number 50 says aqueous solutions of nickel 2 chloride. And so what's the formula for nickel 2 chloride?
NiCl2.
NiCl2. And potassium hydroxide. What's the formula for potassium hydroxide?
KOH.
KOH. Are mixed. So both of these are aqueous. And do you recognize the pattern? The pattern is what kind of pattern is this? Single replacement, double replacement? Double replacement. And so what we're going to have is, in the double replacement, we'll take nickel and hydroxide and potassium with chloride. And so the first product is nickel 2 hydroxide. What's the formula for nickel 2 hydroxide?
NiOH2. Parentheses around the OH.
Potassium with chloride?
Just KCl. You would balance it by adding a 2 to the potassium hydroxide and 1 to the potassium chloride. 2, yeah.
Next, we need to determine the states. And so, this is a salt, what we call salt. Is this a soluble salt or insoluble salt? And so first we look at the cation. This is not a group 1 ammonium. Then we look at the anion. Hydroxides are all soluble or all insoluble?
All soluble.
Well, actually I'm jumping ahead, but hydroxides tend to be insoluble, actually.
Yeah.
Except for which ones?
Group 1.
Group 1, that's not group 1. Ammonium, that's not ammonium. And calcium strontium, that's not calcium strontium barium. So this is a typical hydroxide. Typical hydroxides are insoluble solids. When we form an insoluble solid from aqueous solutions, we call that process formation of a solid, but that's too long, so we call it, shorten it to one word. Formation of a solid is precipitation. So this is, in precipitation we form a solid, and a precipitate is that solid. This is a group 1, potassium is group 1. All group 1 salts are soluble, so this is aqueous. Now this is what we call the driving force for this particular reaction. In double replacement reactions, there are 3 driving forces that we look for. And it just needs 1 out of the 3. But the more driving forces, the better. Okay, this is for double replacement only. The first driving force is precipitation. So if we form a precipitate, then that helps drive the reaction forward. If there's no precipitate, then we look for the next driving force. The next driving force is gas formation. The most common thing that forms gas is carbonic acid. Carbonic acid turns out to be inherently unstable and immediately decomposes to H2O liquid plus. So if I remove H2O from this, what am I left with?
CO2.
CO2 gas. So if you ever form carbonic acid in a double replacement reaction, that is hydrogen with carbonate, then don't write carbonic acid because it doesn't last long. Immediately when it forms, it decomposes into this. So this is what we write as the product. So you shouldn't write carbonic acid in there because it's something that you can never really capture as a product. There are some others that decompose spontaneously. Another one is ammonium hydroxide. So if a product is ammonium with hydroxide, we form ammonium hydroxide, but ammonium hydroxide is unstable. And it automatically decomposes into ammonia plus, okay, so if I remove ammonia from this, what's left over? H2O. So it's going to form ammonia plus water. Now ammonia is tricky because that's not really a gas. That's very soluble. So it's AQ, but a little bit can come off as a gas. So we'll write AQ/gas. You'll smell it coming off. So if we have ammonium hydroxide as a product, let's say it's AB nickel chloride plus Cb, potassium hydroxide is going to yield AB nickel hydroxide. So this is my AD plus Cb, potassium with chloride. If AD or Cb is ammonium hydroxide, don't write ammonium hydroxide. Write ammonia and water because it's going to decompose. And the numbers, you know, when we balance it, let's say we form 2 ammonium hydroxides. If we form 2 ammonium hydroxides, that means we're going to have 2 ammonias and 2 waters. There's one more unstable one. It's H2SO3. What's H2SO3 called? Well, it would be the hydrogen ions with not sulfate. Sulfite. It'd be hydrogen with sulfite, so that's hydrogen sulfite, but we name it as an acid. What acid is this called? Sulfurous acid. Sulfurous acid, unfortunately, is also unstable, and it decomposes into water and SO2, sulfur dioxide gas. Sulfur dioxide. Ammonia is also a gas, but the difference is CO2 doesn't like water, and SO2 doesn't like water that much. Ammonia likes water. So we have a driving force. All we need is 1 out of the 3, and then we're okay. But what was the third one? Did I write the third one up there? No. So let's write the third one over here. The third driving force is going from a stronger acid on the reactant side to a weaker acid. So stronger to weaker acid. Usually I use the abbreviation for stronger acid, I use SA. SA doesn't mean strong, it could be weak also, but just stronger than the product acid. And so SA to WA, stronger to weaker acid. Now, you memorize the 7 common strong acids, right? Or you're in the process of memorizing the 7 common strong acids? There's a lot of memorization. This chapter. Here's an acid chart here. So this ranks the acids in terms of strength on the left. so these are the 7 common strong acids. That one's missing one. You know which one that one's missing? That one only has 6 strong acids. 6 of the 7. This one has all 7. Which one is that chart missing?
Hydrogen chloride?
Yeah, hydrogen chlorate, but it's not called hydrogen chlorate. We call it,
Hydrochlorous acid?
no, not hydrochlorous acid.
Hydrochloric acid.
Not hydro. Hydro, we only use hydro if the anion ends in ide. It's an 8. So if the anion ends in 8, we just use,
Chloric acid.
yeah, so it's called chloric acid. And so that chart's missing chloric acid. So we have the, what's this one called?
Perchloric acid.
HI?
Hydroiodic acid.
Yeah, hydro because it's iodide. And so whenever the anion ends in ide, then we use hydro. This is bromide, so this would be, chloride would be,
Hydrochloric.
sulfate would be
Sulfuric.
sulfuric acid, chlorate would be chloric acid, nitrate would be nitric acid. This is perchlorate, so this would be
Perchloric.
perchloric acid. These are all strong acids. Everything else is weak. But, you know, some of these weak ones are stronger than others. And so they're all ranked here. You can kind of get it. And so stronger to weaker acid, you don't have to memorize these. You know, we don't memorize this chart. We just use it. This chart. Unfortunately, you do have to memorize the 7 common strong acids. So.
Would we ever need to know which of the 7 acids is stronger than the other, or would that
No.
just be like, that's the stronger one?
No.
Like the 7 common ones would just always be like the stronger one if it were as well?
Yeah.
And we don't need to know the strength of the weaker acids?
No.
Okay.
Now, there are some patterns. You know, the question is, do you need to know the ranking? No. But there are some patterns that we can use to help us understand these based on the composition and structure, which we'll look at later on. So many pages open, kept closing on me. Okay, I guess it closed on me, so I have to reopen this. These are pretty good for practice nomenclature, so let's just go ahead and get some practice nomenclature here. A. Calcium. Is a good, poor, non-conductor of electricity.
Or, no, metal. It's good.
It's good. Metals are good. B. Hydrochloric acid is normally what we name it, but take a look. If B, what's C?
That's in solution.
Yeah, and so this is something that's kind of memorized as well. You know, there's a ton of information that needs to be memorized. The easiest way to memorize it is just to do it, you know, daily, if you could. Just review this. One of the things is there's a convention with things like hydrochloric, hydrobromic, and hydroiodic acid. Those are normally gases in pure form. And so the gases we name as ionic compounds. And so this would be HCl gas, which we call hydrogen chloride gas. We name it as an ionic compound. We don't name it as a binary molecular compound, even though this is a binary molecular compound. So we wouldn't call this monohydrogen monochloride, we just call it hydrogen chloride gas. When you dissolve it in water, we form the acid, and the acid we call hydrochloric acid. Now that doesn't hold up for everything. So for example, this NH3, do you know what that's called?
No.
Yeah, this has been happening, unfortunately. I don't know what's wrong with the computer, but maybe somebody knows what's wrong with this thing. Maybe it's this deep sky stacker. What's deep sky stacker, do you know?
It's like an extension or something.
Maybe it's the Internet Explorer page? Or the, what do they call it now?
No, don't. Edge. Thanks. This is called ammonia. Ammonia in pure form is a gas. So NH3 gas versus NH3 aqueous. Do you know what we named those? NH3 gas is called pure ammonia or ammonia gas. NH3 aqueous is called
Ammonium. No?
Still running?
aqueous ammonia. And so it's the same. Are these HCl gas, would you expect that to be a good conductor of electricity?
No.
No. HCl aqueous?
Yes.
Yes. HCl aqueous will, when it dissolves, breaks apart into ions. These are actually molecules of HCl. And so molecules aren't very good conductors of electricity. NH3 is a weird one because NH3 is also a weak base. Weak bases are weak electrolytes.
conductors, yeah.
Yeah. And so what does that do? So we'll need to talk about that probably now. But before we get there, I want to do a couple of more things with this. And so we'll be talking about that. But let me finish this problem, which I haven't finished. This one is going to be called the total, what's it called? Oh, not the total. It's called the full formula equation. There are other names for this. So this is the full formula equation. And then what we're going to write is B. So this is A. B is going to be the total ionic equation. The difference between the full formula equation and the total ionic equation is this. For the total ionic equation, we're going to dissociate the strong electrolytes only. The weak electrolytes and the non-electrolytes, just leave them alone. And so B here, we're going to dissociate strong electrolytes. Don't touch anything else, that is, don't dissociate weak electrolytes and don't dissociate non-electrolytes. So what we're doing is we're looking at the major species. And so nickel 2 chloride, is that a strong electrolyte? Well, strong electrolytes are strong acids. Is nickel 2 chloride a strong acid? No. It's not one of the 7 common strong acids. Is nickel 2 chloride a strong base? Now, nickel 2 chloride is a
Salt.
salt, and is it a soluble salt? Yes, and so we dissociate soluble salts, which means we break that up into ions. What ions does this break up into? Nickel,
Plus 2.
so I'll say nickel 2 plus, aqueous, and,
Cl minus.
yeah, and how many of those do I need?
2.
2 Cl minus AQ. And so that's going to dissociate into the ions, and to keep things balanced, I'll have 1 nickel 2 and 2 chlorides. All right, how about KOH? Is that a strong acid?
No.
Is it a strong base? It turns out it is a strong base, but before that, we say it's a soluble salt, because all group 1 salts are soluble. So if it's a soluble salt, what do? Dissociate it, because we're going to dissociate the strong electrolytes here, and this is going to form 2 potassium ions and 2 hydroxide ions. So essentially what I'm doing here is I'm just looking. If I have a beaker that's labeled NiCl2AQ, what's inside that beaker? So if I have a beaker that's labeled NiCl2AQ, then inside that beaker I have nickel ions floating around there and chloride ions floating around there. They're going to be moving randomly with translational motion, so they're free. Do I have any molecules? Does nickel 2 chloride form molecules? No. What does nickel 2 chloride form? Not molecules. It forms a what type of structure? A lattice. It forms an ionic lattice. And when you dissolve that ionic lattice in water, what happens to the ions in the lattice? They get pulled apart by
The
water. And so the lattice is completely pulled apart, and I'm just left with these free ions floating around in solution. And so in the full formula equation, I'm just looking at the label here. You know, this is nickel 2 chloride. In the total ionic equation, I'm looking at what's inside the water. What's inside the water? I have nickel ions and chloride ions, and I'm not going to find any molecules in there or formula units. And the same thing here. If I have another beaker, that other beaker is labeled potassium hydroxide, AQ. Okay, that's fine. That's what the beaker's labeled. That's the full formula view. But then we dig deeper and we look inside the water. What's inside the water here? I'm going to have aqueous potassium ions. So I'll need to write those in here. And I'm going to have aqueous hydroxide ions. And so the hydroxide ions will be floating around here. But potassium hydroxide, is that a molecular compound or an ionic compound here? This is an ionic compound. It's an ionic compound that forms an ionic lattice. When you put that ionic lattice in water, the water molecules pull it apart because it's soluble. And so I'll have that. Okay, now what I'm going to do is I'm going to mix these two beakers together. And so the nickel and the chloride just go their own way. But then the nickel is going to see hydroxide, and when nickel sees hydroxide, does it like hydroxide? Yeah, nickel likes hydroxide. And so what happens is we end up with all the nickels and all the hydroxides combining. And when they combine, they're going to form a precipitate. And that precipitate is going to settle down. So we're going to get an ionic lattice of nickel 2 hydroxides, packed together. And these are going to form crystals of nickel 2 hydroxide, which will settle to the bottom of the beaker. How about the potassium ions and the chloride ions? And so the nickel 2 hydroxide, is this a soluble salt? No. Is this a strong acid? No. Is this a strong base? No. The strong bases are the soluble hydroxides, not the insoluble hydroxide. And so we leave this one alone. But how about potassium chloride? Is potassium chloride a strong acid? No. Strong base? No. Soluble salt?
Yes.
Yes. And so potassium chloride will dissociate into 2 potassiums and 2 chlorides. these will be dissolved in water, aqueous. And so above this precipitate, the precipitate should fall to the bottom of the beaker, but in the water above this, we should have potassium ions, aqueous potassium ions, and aqueous chloride ions floating around. And so what happened was we switched it. Nickel and hydroxide like each other. How about potassium and chloride? Did the potassium and chlorides come together? No, they didn't come together. And so what we call that is the potassium and chlorides didn't react. So the potassium started off here as potassium ions AQ, and we end up here as potassium ions AQ. So we had potassium ions floating around before the reaction, and now we have potassium ions floating around after the reaction. So potassium is what we call a spectator. Spectators don't participate in the reaction. And then we have chloride ions floating around in water here, and we have chloride ions floating around over there. So chloride ions are also spectators. And so when I mix these two beakers together, the nickels and the hydroxides react with one another. So the nickels and the hydroxides react with one another to form nickel 2 hydroxide precipitate. And so these ions like each other enough to precipitate. This last one is called the net ionic equation. The net ionic equation ignores the spectators and just looks at what's reacting. So what's reacting here are the nickel 2s and the hydroxides. And that forms the nickel 2 hydroxide precipitate here. And everything else is spectator. So we're going to switch here, and we'll come back to these kind of equations in a little bit. But what I want to talk about right now are acids and bases. So you remember the strong acids? And strong acids dissociate in water. And so if I have HClAQ, HClAQ is going to completely dissociate into what?
Hydrogen and chloride ions.
Yeah, hydrogen ions and chloride ions. This is called dissociate or ionize. But there's another process that we can think of. Let me erase some of this. The other process is hydrolyze. And so what we say is a strong acid is a strong electrolyte. Strong electrolytes dissociate or hydrolyze. One thing we know about H plus is it's very unstable. Why is H plus so unstable?
It's just one proton.
It's just one proton. In fact, they call it the proton. And so protons are quite unstable. And if there's water around, which there is, the protons will attack water to form what?
Hydronium.
Hydronium. Well, there's another way of looking at this process. We can take HCl and we can just go ahead and add the water initially. And what this does is it hydrolyzes water. hydrolysis is kind of breaking up water. Although this is kind of weird looking, but we go straight. So the water plucks the proton off to form hydronium, and we're left with chloride. And so there are two ways to say it. Strong acids dissociate, or strong acids hydrolyze. And what distinguishes a strong acid from a weak acid is the extent to which they hydrolyze or dissociate. So a strong acid completely hydrolyzes compared to a weak acid. A weak acid only partially hydrolyzes. So if we take acetic acid, then it partially dissociates into H plus and acetate here. And so in other words, H plus, or the proton, we call acid. And strong acids form lots of H plus, so we'll get good electrical conductivity if we're doing the demo. Weak acids don't supply as much H plus because they only partially dissociate. And so this is what these double arrows mean here. This is uphill. This is downhill here. And so we have a lot of molecules. We don't have that many ions. And so electrical conductivity is not going to be as high as something like this. Something like this has pretty much no molecules, all ions. And so over here, this is the major species, the molecules. Over here, this is the major species, the ions. And the same thing here. Strong acids hydrolyze completely, whereas weak acids partially hydrolyze. And so it's the same thing. Rather than thinking, because free protons like this are unstable in water. So we'll do something like this with acetic acid, which will make hydronium and acetate. But this is quite uphill, and so we don't expect much. And so this is like 99.9%. This is the major. This is the minor. Over here, this is the major. But this is so steep downhill that there's very little minor. In fact, there's negligible minor. And so when we look at this driving force, this is so steep downhill that nothing makes it back up the hill. Whereas something like this, most of them stay down here at the base of the hill, but a few of them can climb up to the top of the hill. Once this falls down the hill, pretty much none of them will climb back up the hill. The hill's too steep, too high to reverse. So, strong acids are going to be characterized by having lots of H plus. Weak acids, we're going to have a lot less H plus in solution. When we look at some bases, bases only hydrolyze. They do not dissociate. So something like, what was the base that we just did? Potassium hydroxide, was it? For potassium hydroxide is actually a solid. And group 1 salts are all solid. And so first, I call this a soluble salt. And
that's going to produce potassium hydroxide, AQ. And so the first step is it's soluble in water. The second step is it's a strong electrolyte. Strong electrolytes do what? Strong electrolytes dissociate in solution. So this is going to dissociate into potassium ions and hydroxide ions here. Then hydroxide ions themselves, this is what we call base. Base is kind of the opposite of an acid. Acid is H plus, and base is OH minus. If you take an acid and you combine it with a base, do you know what you make? H plus plus OH minus makes
Water.
water, HOH, water. And so this is a strong base. Now, bases do not dissociate. So if I have a strong base, which is hydroxide, what we say is hydroxide hydrolyzes water completely. That's what strong bases do. Weak bases partially hydrolyze water. So strong base will hydrolyze water, but when we hydrolyze water here, you know, what the base wants is it wants to pick up an acid. Acid is H plus. Because if we take the base, OH minus, and pick up the acid, H plus, then we're going to form H2O. And so H plus plus OH minus. But if we remove an H plus off water, we're going to be left with hydroxide. So it's the same. Okay. And so if we hydrolyze, if hydroxide hydrolyzes water, then there's basically no change. But that's okay because strong bases will have lots of hydroxide in water. And that's all we need for a base. Weak bases do what? Weak bases partially hydrolyze or partially dissociate?
Partially hydrolyzed.
Partially hydrolyze. So this is a strong base. And whether this goes 0 or 100%, we end up with the same thing, lots of hydroxide. But if we take a weak base like ammonia, ammonia is a weak base, and weak bases do not dissociate, weak bases hydrolyze. Hydro is water, lysis is breaking up water, so hydrolysis is just breaking up water. And so if we take ammonia and water, what do we form? Weak base is partially, so this is uphill. The downhill direction is to the left. Do you know what we form? Well, bases, in this case, this is going to take an H plus. Bases want H plus. And so ammonia is going to take an H plus to form NH4 plus, ammonium. And so ammonia gets converted into ammonium, and water loses an H plus to form hydroxide. And so this is what we form here. But this is uphill. Since this is uphill, we don't form very much hydroxide. And so in strong bases, we have lots of hydroxide. In weak bases, we have a little bit of hydroxide. And the more hydroxide we have, the stronger the base. And so when we did aqueous ammonia, we saw the light bulb light up. It wasn't as bright as sodium hydroxide, but it did light up. It lit up not because of the ammonia, it lit up because of the hydrolysis, which made the ions over here. Hydroxide, which is base. Over here. Okay, so the ammonia is not going to dissociate into ions. Ammonia is this. And so the major species here are this. This is the major. And the minor species here are the ions. This is the minor. And this is uphill. We say the driving force is backwards.
But even though this is uphill, not everybody's the same. Like, if you think about it, like a cup of water. In a cup of water, are all the water molecules moving exactly the same? No, they're all moving in different directions. Even though the waters are moving in different directions, are they all moving at the exact same speed? No, they aren't. And so some of the water molecules are moving a little slower, some of them are moving a little faster. Just like if you have a whole bunch of people on bicycles, are all the bicyclists going to make it up the hill? No. In fact, it depends on how steep the hill is. Let's say this is a pretty big hill. So maybe 99.9% of the bicyclists stay at the bottom of the hill. So we'll just say 99% might stay at the bottom of the hill, and then you have 1% that might be aggressive enough to make it to the top of the hill. And so we end up with about 1% over here. Sometimes the hill isn't as steep or as long, and so sometimes we get more. Sometimes we'll get like 10% make it up, 40% make it up, you know? Whereas in a strong base like this, everybody makes it. Well, this is the same thing, so everybody's going to make it. Going downhill, you can get even, you know, the water molecules with even the lowest energy to get you down the hill. So ammonia is what? A good conductor, a poor conductor, or non-conductor of electricity? Ammonia aqueous ammonia. Poor conductor, right? Or, you know, moderate. I mean, it lit up the bulb. It's a poor conductor because it doesn't have as many ions as something like potassium hydroxide. Potassium hydroxide would be good. Ammonia, is that molecular or ionic?
Molecular.
It's molecular. But when we undergo this hydrolysis, that's where we form ions. The ions can conduct electricity. Would you expect ammonia and water to conduct electricity? No. And so it's because of this hydrolysis, that's the reason why it conducts. This one should conduct electricity. What is this called?
Magnesium chloride.
Yeah, magnesium.
Magnesium chloride
2.
Is it liquid?
liquid. Liquid magnesium chloride is called molten magnesium chloride. So if you melt the magnesium chloride, it's going to conduct electricity because you break apart the lattice, so now the ions are mobile. But you don't have any water there, and so it's not aqueous, it's just liquid. Should that be a good conductor or a poor conductor? Or non-conductor?
Very good.
Very good
Yeah,
conductor,
because
What if we cool it down and it freezes? It would be non-conductor.
Yeah.
Like this KCl solid,
It's not conductive.
yeah, non-conductor. KCl is called,
Ionic.
it's an ionic compound, potassium chloride. H2S, is that a molecular compound or ionic? H2S.
S is
Molecular.
sulfur.
Hmm?
Molecular.
It's molecular. H2S forms molecules. So H2S gas consists of molecules of H2S. Is this a binary molecular compound?
Yes.
Yes. This is a binary molecular compound. It just consists of hydrogen, the element, and sulfur, the element. So this is a binary molecular compound. So if we have a binary molecular compound, we should use the rules for naming binary molecular compounds. Using the rules for naming binary molecular compounds, this would be called
Hydrogen sulfate.
well, dihydrogen is correct. Dihydrogen
Sulfide.
mono
Sulfide.
sulfide. Dihydrogen monosulfide. But if your binary molecular compound is an acid, and how do I know this is an acid?
Cause the hydrogen.
Because it starts with H. If your binary molecular compound is an acid, then we do not use the binary molecular compound rules. You know what we use? We use the ionic compound rule. So rather than calling this dihydrogen monosulfide, we just call this hydrogen sulfide. Because we know what sulfide is -2, so we know we have two hydrogens. So this is called hydrogen sulfide gas, and it's pure hydrogen sulfide. It's quite toxic. You wouldn't expect it to conduct electricity because it consists of molecules, no ions, this molecules of H2S. Whereas if you dissolve it in water, we don't call it hydrogen sulfide. You know what we call it?
Sulfic acid.
Sulfic acid would be if it's 8,
Yeah, if it's 8.
but it's ide. If it's ide, then we have to have
Sulfuric acid.
yeah, but we have to have a prefix. Whenever we have ide, chloride,
Hydrosulfide.
hydrochloric acid. Sulfide,
Hydrosulfide.
hydrosulfuric acid.
Sulfuric acid.
So in the first one, we name it as ionic compound, hydrogen sulfide. This is for acids. In the first one, we name it as ionic compound, hydrogen chloride, not monohydrogen monochloride, hydrogen chloride as an ionic compound. In the second one here, it's aqueous, so we call this hydrochloric acid. We're going to call this one
Hydrosulfic. Hydrogen sulfic.
yeah, hydrosulfuric acid or hydrosulfuric acid. They chose hydrosulfuric acid because it just sounds a little better. So, is hydrosulfuric acid a strong acid?
Yes.
Yes.
Wait. I just.
What were the?
Oh, that's sulfuric. No, hydrochloric acid is strong.
Hydrochloric acid is strong.
But
Hydrosulfuric acid, is that strong? Is that one of the 7 strong acids here? No. And so hydrosulfuric acid must be weak. If it's a weak acid, then that means it's a weak electrolyte. If it's a weak electrolyte,
It's a weak conductor.
it's a weak conductor. Yeah. And so we say a weak conductor of electricity, but I don't know if poor is the best word for that, because it could still be a weak conductor and kill you. I mean, tap water would be poor. It would still be electric shock hazard. And so we'll just use poor for this. Now this is a proper binary molecular compound. It's not an acid, it's just a regular binary molecular compound. When we look at this binary molecular compound, what would we name it?
Which one would we name it?
I. P4O10, name.
Tetraphosphorus decaoxide.
Yeah. Tetraphosphorus decaoxide, but decaoxide is double vowel, so usually they try to get rid of the double vowel by removing the one. And in this case, they remove the A. So this is called tetraphosphorus decoxide. It's like the double vowel carbon monoxide. We don't call it carbon monoxide, we call it carbon monoxide. And so it's the same type of situation that, is this going to conduct electricity?
It's a
No.
solid now.
It's a solid, so there's no mobility and
Not a metallic.
there's no charge.
Charge, yeah.
Yeah. So it doesn't conduct electricity. So insulator. J. Now we have the same situation here. Aqueous, we call it the acid. So this would be called
Acetic acid.
acetic acid.
Yeah.
This is acetate goes to acetic acid. This is pure. This is pure acetic acid, which is liquid. What do we call it?
Glacial.
Yeah, good.
This is called glacial hydrogen acetate or acetic acid?
Acetic.
Yeah, this is called glacial acetic acid. You know, this didn't conduct any electricity, but it's still called glacial acetic acid. And so there are some exceptions. These aren't laws, these are just rules. So this is a hydrogen sulfide, but this is not hydrogen acetate. This is going to be acetic acid, glacial or pure acetic acid. So sometimes we do this, sometimes we don't. Typically when we do it for gases. So HCl is a gas, H2O is a gas, this is a liquid. Pure sulfuric acid is a liquid, but we call it pure sulfuric acid. We don't call it hydrogen sulfate. Did the acetic acid conduct electricity? Yeah, but not that well. This is weak. Weak acids are weak conductors. They're weak electrolytes. How about the pure acetic acid? Pure acetic acid didn't conduct at all. No. What we need is we need water to pull off the proton, the hydrogen. That's what we need, but we didn't have it. What's this one called? Yeah, but is copper fixed charge or variable charge? Copper 2 sulfate. And so this is copper 2 sulfate. Is copper 2 sulfate soluble? It must be because it's an AQ. And so what that means is this. It means sulfates are all soluble or all insoluble? Soluble except for which ones?
Bromide,
Starting with silver.
Yeah,
silver, lead, mercury,
calcium, strontium,
Yeah,
bromide,
good. Silver, lead, mercury, calcium, strontium, barium. Is that going to be a good conductor? Soluble salt? Yes. Soluble salts are strong electrolytes. So this is going to dissociate into ions, copper 2 and sulfate. So it's going to be a good conductor of electricity. All right, let's speed it up. Maybe name for this. Here we don't see AQ or gas. So we're just going to name this as the acid. What would you call that HI? As the acid. Hydroiodic acid. Strong electrolyte, weak electrolyte, or non-electrolyte?
strong electrolyte,
Strong. This one,
rubidium sulfate,
rubidium sulfate. Ionic or molecular?
ionic,
Ionic. This is molecular. This is ionic. This would be all group 1 salts are soluble. And so rubidium is group 1. And so we don't even have to look at sulfate. This is soluble. Soluble salts are strong.
conductors.
Yeah, strong electrolytes, strong conductors. What's this? HNO2. Is that nitrate or nitrite? That's nitrite.
Yeah,
So this
nitrite.
must be nitrous acid. Is nitrous acid one of the 7 strong acids? No, nitric is. Nitrous isn't. So this is weak acid. Weak acids are weak electrolytes. What's this? This you could call hydrogen cyanide. If this were gas, we call it hydrogen cyanide gas. Hydrogen cyanide gas is, do you know what they use that for? The state of California use that for? No? You don't know? This was the gas they used in the gas chamber. So I think if you visit San Quentin on a tour,
for
something.
execution.
Yeah. Cyanide is like carbon monoxide. You know, carbon monoxide binds to your hemoglobin and prevents oxygen from binding. Well, cyanide's the same thing. Cyanide binds to your hemoglobin and prevents oxygen from binding. So
Is that still an allowed course of execution or?
no.
Okay, I didn't think so. That'd be very cool.
I don't know. It just sounds, you know,
Carbon, if you were to die by carbon monoxide poisoning, which lots of people do every year, you hear about it, people just get sleepy and sleepy and sleepier, and then they dead. Okay? I wonder if it's the same thing with hydrogen cyanide. You get sleepier and sleepier, and then
It is.
it is. Okay. Yeah. Oh, I prefer neither. Actually. But anyway, is that a strong acid? Because what would we name this as an acid? If this were AQ, we'd call it. And how do I know it's an acid? I know it's an acid because it begins with an H. Things that begin with an H are acids. And I'd call it
Cyanic, right?
no iodide. Iodide is called
Ionic.
what's the name of this acid? Hydroiodic.
Hydrocyanic.
Chloride is hydrochloric. Sulfide is hydrosulfuric. Therefore, cyanide with a D is
Hydrocyanic.
hydrocyanic acid. Hydrocyanic acid is weak. And so hydrocyanic acid would be a weak acid, which would be a weak electrolyte. What's this called?
Sodium carbonate.
Sodium carbonate's a group 1. Sodium's group 1, the alkali metals. Therefore, it's a soluble salt. Soluble salts are strong. Ammonia is a weak base. Weak bases are weak conductors. But ammonia is molecular, and so what conducts? Molecules are neutral. And so what conducts is ammonia undergoes hydrolysis to form a small quantity of ions here, and that's what conducts here. What's this one called?
Potassium permanganate. There you go.
Yeah, potassium permanganate. Potassium permanganate in the solid form forms purple crystals. Are those purple crystals soluble in water or insoluble in water? Soluble. Potassium is a group 1, so this is a soluble salt. Soluble salts are strong, right? Strong acids, strong bases, and soluble salts are strong electrolytes. So this is a strong electrolyte. This should conduct quite nicely. But you should be careful with this one. Why? This one is kind of dangerous. Potassium permanganate. It's kind of dangerous. It's not like potassium chloride. Potassium chloride is not dangerous. Potassium iodide, potassium iodide is a little bit more reactive. But potassium permanganate is a little bit dangerous because it's a soluble salt, but that's not the reason it's dangerous. It's dangerous because
The manganese.
it's because the permanganate. What's special about permanganate? Permanganate's MnO4 minus.
So it's a good reducer.
Is it a good reducer
It
or a good
reduces-
oxidizer?
If it's negative, it means it has extra electrons. So
Yeah, it has extra electrons, but who has the extra electron?
the potassium.
No. Who has the extra electron is oxygen,
Oh, yeah.
but is that really an extra electron, or is that the electron that, is it going to be easy to take that electron away from oxygen? No. And so this is kind of stable as is. How about manganese?
It has to be a +7.
Manganese has to be a +7. Is a +7, is that a common
No.
charge?
No.
No, it's not a very common charge. In fact, that's very high, isn't it? And so this is a powerful oxidizer. If you want to make poisonous gas, you take some potassium permanganate and mix it with salt, sodium chloride. You know what you'll make? If you take potassium permanganate and mix it with sodium chloride. And this is how you make this in laboratory. Sometimes we want to make this gas in the lab. Potassium permanganate plus sodium chloride, what do you think it produces?
Sodium permanganate and potassium chloride?
Yeah, but there's no driving force here. So you might say there's no reaction. So you get some potassium chloride and some sodium permanganate. Both of these are aqueous, so no precipitate. Neither of these are gases, so no gas. And they aren't acids, so there's no driving force. So we might say NR, but that would be a mistake because you should say NR for double replacement. There's actually a redox reaction that occurs here. And so when we inventory this, we have potassium ions, permanganate ions, sodium ions, and chloride ions, and water. Do you know what the strongest oxidizer is? Potassium ions?
No.
No, terrible oxidizer. Sodium ions?
Four.
Terrible oxidizer. Water? Pretty weak. Permanganate? Yes. Permanganate's a good oxidizer. And permanganate, well, what has electrons? Chloride's happy as is. And water has electrons, but those are tightly held too. But permanganate's very aggressive. And what ends up happening is permanganate attacks chloride and forms, well, when chloride loses electrons, you know what it forms? It forms chlorine. And so what we do is we use this to generate chlorine gas in the laboratory. So. Just like, I think in the gas chamber, they take potassium cyanide and mix it with acid. When they take potassium cyanide and mix it with acid, then they generate the gas on demand. And so they can make this stuff as needed. Well, we can make chlorine gas as needed. We need one more ingredient for this, but I'll talk about that more later. We need some acid here, and then it really works well. So, solid potassium permanganate, wouldn't conduct electricity very well, but this is soluble in water, and so it'd be strong, soluble salt. How about iron 3 chloride? Chlorides, bromides, and iodides are all soluble except for
What,
silver, lead, and mercury. Yeah. So it's a lot of stuff to memorize. So if you don't have a good handle on this, or if you aren't starting to develop a handle on this, then probably what you should do is you should review it every day. That's helpful. I struggled with memorization a lot because I don't have very good memory. But when I started reviewing things every day, then it became a lot easier. And so this is a soluble salt. Soluble salts are strong electrolytes. And the name of this?
Iron chloride.
Iron trichloride.
We use iron trichloride if it were binary molecular, but this is not molecular. How do I know this is not molecular?
It's
It's a metal.
with the
Yeah, if it were non-metal, yeah, iron trichloride, if iron were non-metal, but iron's a metal.
yeah.
And so we have to name it by
the ionic rules.
ionic rules, and this would be called iron 3 chloride, because there are two iron ions, iron 2 and iron 3, so this is iron 3 chloride. Iron Roman numeral 3 in parentheses, Roman numeral in parentheses, chloride. Do you recognize I?
CH3, CH2OH. That is ethanol. Good. This morning, nobody remembered it. Yeah, not one person. So then I was thinking, even though I wrote this yesterday, but you know, you lose memory so fast. They say, what was it, 30 or 60% of yesterday's memories are gone, you know, the next day. Yeah. So that's why, like, when I was a student at UCLA, I tried to have no back-to-back classes. You know, because if I had a back-to-back class that was very difficult, one, because it's a big school, so to get from class to class takes some time. You know, a lot of people ride bikes or other ways. I actually had a motorcycle, so I could hop on the motorcycle and go to the other part of campus, which is nice. Or a scooter would be nice too, you know. UCSB, it's all bikes. You know, they have bike paths that run all through UCSB. At UCLA, they don't have bike paths. If you ride a bike, it's kind of treacherous because there are lots of people walking. But I'd like to keep some open time after class so I could immediately review it, you know. That way I wouldn't forget it, and so, or forget as much. And so if I could review my notes right after class and then do that, then I capture a lot more material. So that's why I preferred that. But we have ethanol here. Uh-huh.
Why isn't ethanol written like C2H5OH?
This is good. This is good memory because C2H5OH was how it was written in the lab. Right? There are 3 ways to write ethanol
Oh, that's fun.
that are common.
Well, then it's this way, and then just
CH3, CH2OH. This is called the condensed structural formula. And then what they like to do is they'd like to shorten this to C2, 2 carbons, and 5 hydrogens, and then an OH. And so this is a condensed structural formula. But it's condensed, you lose a little bit of information. And then we could condense this further to C2H6O. Do you recognize this as being ethanol? No. In fact, when you write the formula here, we don't know what it is because there are multiple compounds that have the same formula. And so this might be ethanol, or it could be something called dimethyl ether. And ethanol you could drink, but you can't drink dimethyl ether. And so if somebody said, I'm going to give you some of this, I wouldn't drink it. Yeah.
So does the original and ultimately correct one mean that there's like a carbon with 3 hydrogens attached to a carbon with 2 hydrogens attached to an OH?
Right.
Okay.
And so we can see that this carbon's going to have 3 hydrogens attached to it, and the next carbon will have 2 hydrogens attached to it, and then we'll have an OH like that. And so this is the structure, and it's just condensed. So this is why I prefer this formula here. It takes a lot more space, but at least it's not dimethyl ether or ethanol. Ethanol, do you know what ethanol is called? Let's see, it's CH3C, is this it, C2H4, no, it's not going to be ethanol. Yeah, well, this would be an aldehyde. A ketone would have another carbon here. And so this one's fine, you know. But all of them mean the same thing. So ethanol, is that a Molecular or ionic compound? Molecular. And ethanol is water-like because it has this COH thing. The COH we call alcohol, the COH here. And so this part of the ethanol molecule is like water. This part is not. But it's enough so that ethanol is quite soluble in water. And so, is that a strong acid? No. Is it a strong base?
No.
Soluble salt?
No.
Weak acid?
No.
Weak base? Heavy metal salt? And therefore, it's going to be a non-electrolyte. If it's not one of those, it's got to be a non-electrolyte. And so, when we have ethanol in water, it just consists of ethanol molecules. Ethanol molecules have plenty of mobility. And if it's concentrated enough, we have plenty of number. So we have lots of ethanol molecules, and they have mobility. What are they missing? They're missing something. They're not going to conduct electricity because they're missing
Something to disassociate them?
well, you need three things to conduct electricity. You need mobility, and you need quantity, number, and you need, it's the third thing we need. Charge. They're missing charge. We need water, but I'm not going to have the fourth. Because water, if electrolytes are looking at in water. So we're missing charge. Ethanol is neutral. The water molecules aren't going to break this apart. This is not hydroxide. If this were metal rather than carbon, then we'd call it a hydroxide. But this is a carbon, and therefore this is not a hydroxide here. We'll talk more about the bonding later. Okay, what's this next one? Strontium hydroxide. That's good. Strontium hydroxide is a salt. Is that a soluble salt or insoluble salt? Yeah, because hydroxides are insoluble except for
Group 1 and 1.
group 1 ammonium and calcium. Oh, wait a minute.
So it's soluble.
Yeah. Strontium hydroxide is a soluble salt. And therefore,
It should conduct.
it should conduct. Soluble salts are good conductors. So this is a strong electrolyte. Soluble salt. In fact, all the soluble hydroxides, what are the soluble hydroxides? The group 1, sodium, lithium, potassium, cesium, rubidium. All those hydroxides are what we call strong bases because they are all soluble. They lead to lots of hydroxide in water. And strontium is a strong base. Barium hydroxide is a strong base. And strontium, barium, and calcium. Calcium hydroxide is a strong base. But the other hydroxides are not strong bases. So if you had magnesium hydroxide, is that a strong base? Well, magnesium hydroxide is soluble or insoluble? Magnesium hydroxide, soluble or insoluble? Insoluble. And so magnesium hydroxide, we don't consider a strong base. Magnesium hydroxide is not going to produce nearly as much hydroxide. So anyway, this is a soluble salt, strong electrolyte. How about this? What's this called? Ammonium nitrate. Ammonium nitrate? Yeah, all ammonium salts are soluble. Not only that, all nitrate salts are soluble. So this is for sure soluble. Soluble salts, strong electrolyte. So it's going to dissociate into ammonium ions and nitrate ions. Some of these are a bit more complex than, some of these are a bit more complex.
Did he say?
Because this, do you see ammonium here? Ammonium is known as a weak acid. But you know, it's kind of a weak acid, but it's stronger than this acid. What's HCN called?
Hydrocyanic acid.
So ammonium is stronger than hydrocyanic acid, but weaker than some of these other acids here, including this one, acetic acid. And so it's ammonium. But we know that weak acids are weak electrolytes, right? Weak conductors. But if I have ammonium nitrate, it's a strong conductor of electricity. And so what's going on there? What's going on there is we think in two steps. So ammonium nitrate itself is a salt, and it's a soluble salt. And so if I had solid ammonium nitrate, which is a white solid, and I place that into water, I know it's dissolved into ammonium nitrate AQ. Soluble salts are strong electrolytes. And so if I have ammonium nitrate, it should dissociate into ammonium ions and nitrate ions. And strong electrolytes dissociate completely. Weak electrolytes dissociate partially. And so here, ammonium itself is a weak acid. So up until this point, I'm thinking soluble salt, soluble salt. In the next step here, ammonium, weak acids do what? Weak acids partially dissociate or partially hydrolyze. And so what's going to happen with ammonium is this. We're going to get a next step. And the next step is it partially dissociates into hydrogen ions and ammonia, or it partially hydrolyzes. And so when ammonium hydrolyzes water, it partially hydrolyzes to form hydronium and ammonia. So both of these are the same thing. And so this is the weak acid part of it here. You know. And so yes, ammonium nitrate is a weak acid, but first it's a soluble salt and then it's a weak acid. Does that make sense? So this is going to be a strong conductor of electricity. I don't know how much electricity you want to conduct with ammonium nitrate, because ammonium nitrate is also known as a what? Explosive material. You probably don't want to be conducting too much electricity through that. A solution. Although the solution's safer because, you know, of the water. The water will quench off heat that's generated. What's this next one? Sulfuric acid. Sulfuric acid is a strong acid? Strong acids are strong electrolytes. Strong electrolytes dissociate or hydrolyze completely. But this one's complex too. Do you guys remember? What does it dissociate into? So H2SO4, strong acid, dissociates into what? Well, this is, let's say this is already aqueous here. So it dissociates into one hydrogen or two hydrogens. This is what we call a diprotic acid, as it has two acidic hydrogens or two protons it can give up. And so are both of the hydrogens going to break off at the same time or one at a time? One at a time. So first step is we form hydrogen ions and HSO4 minus, which is called hydrogen sulfate or bisulfate. And so this is going to be a great conductor of electricity because we're going to form lots of ions. But we know this one, HSO4 minus is a weak acid. And weak acids do what? Partially dissociate. It's not one of the 7 common strong acids. So HSO4 minus is going to partially dissociate into another H plus and an SO4 2 minus. And so this is what we end up with here. So we're going to get a little bit more ions, about 10% more. You know, it's going to be about a 90 to 10 ratio. 90%, 10%. You don't need to know the ratios. In Chem 1B, we calculate the ratios.
Oh, joy.
Something to look forward to.
Yeah, it's something to look forward to. You can calculate it and then write down the ratios. So it's a strong electrolyte here, it's a weak electrolyte here. Step 1, strong electrolyte. Step 2, weak. Altogether, it's going to conduct electricity very well. Let's just get some more nomenclature practice here. What's this? Called? Potassium cyanide. It's an ionic compound, so we call it a salt. And is it soluble? Yeah. And so this is going to dissociate into potassium ions and cyanide ions. This one? Lead 2 chloride. Lead 2, no, we don't know. Chloride, bromide, and iodides are all soluble except silver.
Mercury, lead.
No. Chlorides, bromides, and iodides are all soluble except silver, lead 2, and mercury 1. So they just call it silver, lead, and mercury. And so this is insoluble. Insoluble means the major species is just going to be PbCl2 solid. You know, it doesn't dissolve. So maybe a little bit this is dissolved, but most of it stays as PbCl2 solid. Yeah, this is called hydrogen bromide or hydrobromic acid. Bromide is the hydro. So hydrobromic acid, strong. So we're going to get H plus and Br minus. Cesium hydroxide is soluble or insoluble? Hydroxides are insoluble except group 1, ammonium, and calcium, strontium, barium. In fact, all group 1 salts are soluble. So cesium, this is going to be soluble. So it's going to dissociate into cesium ions and hydroxide ions. Ammonia,
Oh, it's group 1.
group 1 salt, so this is soluble salt. Cesium ions and hydroxide ions. Ammonia, weak base. So the major species in ammonia is just going to be ammonia AQ. You know, it's uphill to form ammonium and hydroxide. We need the water. Because bases don't dissociate, bases hydrolyze. So we need the water. And so ammonia plus water is going to give us ammonium plus hydroxide. This is the major species. Yeah. This is more like 99.9%, and only about 0.1% hydrolyze here. Oxygen. What's that? Strong acid? Strong base? Soluble salt? Weak acid, weak base?
heavy metal solid? No. This is a non-electrolyte, so the major species will just be oxygen, O2. It doesn't dissociate. H3PO4 is called H3PO4? Phosphoric acid. That's correct. A phosphoric acid is what we call a triprotic acid. Triprotic acid has three. Like sulfuric acid is called diprotic acid. It has two, what we call acidic hydrogens. Phosphoric acid has three. Is phosphoric acid a weak acid or a strong acid?
Strong. No. It's not one of the top 7 that's weak.
It's weak. It's a weak acid, so the major species is just this. Do all three hydrogens break off at the same time? No. In fact, this is going to be a 3-step process. In the first step, we form a little bit of this, H plus and H2PO4 minus. H2PO4 minus is called dihydrogen phosphate. And then the dihydrogen phosphate, the H2PO4 minus, can dissociate, but it becomes even weaker. With each step, it becomes weaker and weaker. The next step is weaker. We're going to form H plus and this. HPO4 2 minus is called monohydrogen phosphate. We don't use bi because there would be 2 bytes. You know, we can't call this one biphosphate because then we'd run out of prefixes for this one. So this is dihydrogen phosphate, this is monohydrogen phosphate. And finally, monohydrogen phosphate can lose that hydrogen as well. And this is very weak to form another proton and phosphate. So actually there are 3 steps in this. But they're all weak, and so the major will be H3PO4, AQ, aqueous. All these are aqueous. All right, let's stop here. We'll take a break and then continue after the break.
Right. So we treat it as a salt first, and a base second. So
Were there
salts
any other questions?
dissolve into the water. So we do the
Is there a
dissolving.
chart,
It's gonna break
this
apart.
one that you found?
Once it breaks
That-
apart, it
Yeah.
produces hydroxide
Did you post it in
because this is a
the Canvas
downward
thing, or did
or
that
downhill
find it during the course?
driving force. It's gonna be a strong
Yeah.
base.
Oh, thank you.
Because bases you can define them as
I just posted it today.
when they hydrolyze, they produce the hydroxide, whereas you can define the acid when it hydrolyzes, it produces
Let me make sure.
hydrogen.
Yeah. It should be in the week 7 module.
And then that combines with water to create
Yeah.
H3O.
Yeah, my brain hurts. Sick.
All right, let's just finish these off. H is called aluminum sulfate, which is an ionic compound, metal and nonmetals. Is it a soluble ionic compound or insoluble? So sulfates are all soluble except for silver, lead 2.
Mercury,
Yeah. So it just is silver, lead, mercury, calcium, strontium, barium. And then I just remember lead is lead 2 and mercury is mercury 1 unless you repeat it. And then it's mercury 1 and mercury 2. So this is soluble. A soluble salt is going to dissociate into ions. What ions does it dissociate into? Aluminum ions and sulfate ions. Normally we try to keep the ratios the same because how many aluminum ions am I going to form for every aluminum sulfate? 2. And how many sulfate ions? 3. And we don't want to forget the charge. The charge is most important.
And so the major species are gonna be 2 aluminums and 3 sulfates for every aluminum sulfate formula unit that dissolves. We call this a formula unit, we wouldn't call it a molecule because it's ionic. What's this called? Zinc hydroxide. That's correct. Zinc is fixed charge to +2. Hydroxides are all insoluble except for
Except for
group 1, ammonium,
calcium,
calcium, strontium, barium. This is not one of those exceptions, so this is insoluble. So the major species here is just zinc hydroxide solid. It's not going to dissolve, and if it did, just a tiny fraction would dissolve. And so we'll just say zinc hydroxide solid would be the major species. J is sulfuric acid, strong acid, strong electrolyte. So what are the major species here? Not exactly close. The major species are going to be hydrogen ion and what, sulfate? Hydrogen sulfate ion, also known as it's oddly enough, hydrosulfuric acid is this, H2SAQ. That's hydrosulfuric acid. This one's known as hydrogen sulfide, is an acid anion, or starts with a B, bisulfate ion. You should know bisulfate is very common. In fact, people call it bisulfate more than people call it hydrogen sulfate ion. So those would be the major species there. We don't, H2SO4 is molecular, it's all nonmetals, but we don't expect it to find any molecules because it's strong acid. Strong acid is going to dissociate, break apart. We recognize this one, CH3CH2OH is called ethanol, and that's a non-electrolyte. And so it's just, the major species are just going to be ethanol molecules in water. The molecules aren't going to break apart, whereas H2SO4 molecules definitely break apart. Ethanol molecules don't. Do water molecules break apart? It's a non-electrolyte, so. So the major species in water is just water molecules, not hydrogen ions and hydroxide ions. Water, remember, our deionized water is pretty much an insulator. So there's some practice reactions. In the supplement. These supplement problems are pretty challenging. You have the chart, so you asked me, is the chart I gave you the best? I think so.
Where's that?
This is in the supplement. This is page 52 of the supplement.
Just posted this. Taking it good.
Oh, okay. I'm just.
This is good. Actually, the chart for the acids and bases that I posted on Canvas is this. I just eliminated the names. You should know the names of these. But here, if you want to know, if you want a list of the names of the acids, then the formulas, it's here. This is page 55 of the supplement. Page 52.
Redox 6. Okay.
When we go to net ionic equations, NIE1, these are pretty hard. So I'm going to start with some
ones that are more straightforward. So we did number 50. Let's do number 52. Copper 2 sulfate in sodium hydroxide solutions. Whenever you see solutions, that's aqueous. So both of those are aqueous, are combined. Why don't you try that? Figure out from the periodic chart pattern, or two, you just memorize it. You know, and whatever technique you have for memorizing it, that's what you work at. And so sulfate, the way I memorized it, I just wrote it over and over and over again until I had it memorized. That takes time. You'll have to have it memorized by the midterm. And so it takes time. So if you don't have any of these memorized, you better start soon. Otherwise, it's going to be trouble, I think. And so sulfate, SO4, 2 minus. And then it's just a 1-to-1 ratio because they're balanced. So we have that. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. But we already know this is soluble. How do I know this is soluble without even looking at the solubility rules? Do you know how I know it's soluble without looking at the solubility rule? Because they tell me it's a solution. If it's a solution, that means it's got to be dissolved in water. And so this has got to be dissolved in water, aqueous. Unfortunately, when we get to chemical reactions, this is the critical step here, because if you get the wrong formula, then the whole thing is wrong, you know. And so you want to try to get the nomenclature down. Okay, what's the sodium ion? Na plus. And how did you figure out the charge on the sodium? Yeah, it's group 1. What happened to it? And then hydroxide is just one of those ones you just got to memorize. And so hydroxide, there's no easy way around it. You just have to, I think writing this down over and over is good, or flashcard or whatever you want, but it's OH minus. And therefore, this is also 1-to-1 already, and so sodium hydroxide is just NaOH. And this is a solution. Solutions are automatically AQ. And so that would be it. Okay, next, do you see what type of pattern this is? Is this a single replacement or double replacement type pattern? Double replacement. And so we can easily predict it from the names. It's easy to predict it from names because we'll have copper 2, but rather than with sulfate, we'll have copper 2 with hydroxide. And so the first product is going to be copper 2 hydroxide. Well, here's copper 2, here's hydroxide. What's the correct formula? Yeah, we need 2 hydroxides. Why?
Because copper is 2 plus.
Yeah. Copper is 2 plus, so it has to balance out the charge. And then we're going to form sodium sulfate. Sodium sulfate. Sodium sulfate, what's the correct ratio of sodiums and sulfates? Na2 SO4. And so now we need the solubility rules. Because over here it didn't tell us if these were solutions or precipitates or gases, whatever. And so when we look at copper 2 hydroxide, this is not group 1 ammonium. And so we go to hydroxide. All hydroxides are insoluble except for group 1 ammonium, calcium, strontium, barium. So this is not one of the exceptions, therefore it's insoluble. Insoluble means solid, which means precipitate. So we're going to form a precipitate of copper 2 hydroxide. How about sodium sulfate? Sodium is a group 1 because sodium's in the first group, and therefore this is soluble. If it's soluble, it's aqueous. And so we're going to have a driving force for this. All we need is one. DF stands for driving force, so precipitate is the driving force. So this is a downhill reaction. If there's no driving forces, then it's an uphill reaction, and we don't expect it to happen. So we need a driving force to make it go downhill. But it's not balanced. We got to balance it. So go ahead and balance it, and then we go to the next step.
Put a 2 on the sodium hydroxide.
A 2 on the sodium hydroxide, yeah, and it's balanced. Step B is we dissociate what? We dissociate the
Copper sulfate.
strong electrolytes only. Leave everything else alone. The strong electrolytes consist of the strong acids, strong
Bases.
and
Soluble salt.
soluble salt. So copper 2 sulfate is a
Salt.
salt. It's a soluble salt. And so what does this dissociate into?
Copper 2. Sulfate.
Yeah. Sodium hydroxide is the number one most common strong base. But we don't consider it a strong base at this time. We consider it a group 1 salt. Group 1 salts are all soluble. And therefore, I'm not thinking in terms of strong base, I'm thinking in terms of group 1 salt. Group 1 salt is going to be 2 sodium ions and 2 hydroxide ions. And so it's a soluble salt. Whereas the next one, copper 2 hydroxide, is a insoluble salt. Insoluble salts are not strong electrolytes, so we leave it alone. Don't do anything to copper 2 hydroxide. The major species is copper 2 hydroxide solid. And then sodium, well, it's a sodium salt. All sodium salts are soluble, so we're going to dissociate this into 2 sodium ions and 1 sulfate ion. And so this one we call the total ionic. This one we call the complete. I abbreviate this one. So the first one I call the CE, which means just the complete equation. The second one I call the IE, which means the ionic equation. And the third one I call the NIE, which stands for net ionic equation. Net ionic equation is we just eliminate the spectators. Were there any spectators here?
Yeah.
Yeah. Yeah, the sodium is a spectator. And any others? The sulfate. And so this eliminates the spectators, the species that don't react. And the species that react are copper 2 ions combined with 2 hydroxides to form copper 2 hydroxide solid. And so the copper ions will combine with the hydroxide ions to form a precipitated copper 2 hydroxide. That would be the NIE. So, any questions on this one here? Now, one of the biggest mistakes is that people get the driving forces mixed up. That is, the driving forces for double replacement, which is precipitation, gas formation, or stronger acid to weaker acid, are not the same as the driving forces for single replacement. The driving forces for single replacement are the activity series. And so you could have a gas form in a single replacement, it doesn't mean anything. You could have a precipitate form in a single replacement, it doesn't mean anything either. The only thing that's significant in a single replacement is going from more active to less active, going downhill that way. Although it may help to form a precipitate, it may help to form a gas, it's not the driver of the reaction. So let's take a look at the next one, which will be 54. A piece of solid nickel metal is put into an aqueous solution of lead to nitrate, I think that was. Lead 2 nitrate, 54. A piece of solid nickel metal is put into an aqueous solution of lead 2 nitrate. I'll give that one a shot and see. Try 56. Solutions of hydrobromic acid and potassium carbonate are combined.
So it makes sense if it became carbonic acid,
Yeah.
because this is a strong acid, so it goes to strong with this is right? That would be for double replacement.
That's what.
What did you guys get?
Hydrobromic acid plus potassium carbonate.
Okay, what did you get for the formula for hydrobromic acid?
That's what it says. So HBr,
Potassium carbonate?
K2C. Yeah. Like that.
Very similar.
Oh, no.
What did it form?
Potassium
Well, I always do it the same. I go hydrogen with
CO3.
carbonate. Hydrogen carbonate, what's the formula for hydrogen carbonate?
Can we make carbonic acid, or does it have to be hydrogen carbonate?
No, hydrogen carbonate and carbonic acid is the same thing.
Oh, okay, so H2CO3.
H2CO3 can. Okay, this is the biggest mistake with carbonic acid. The biggest mistake is to leave it as carbonic acid. We never leave it as carbonic acid. Why?
It off-gases.
It dissociates.
It doesn't dissociate. It's a weak acid.
It produces a gas, because it's not stable.
Yeah, it's unstable. It decomposes, as we say. And to show that it decomposes, there are different ways you can do it. One, you don't write it here. Or two, you just draw an arrow through it saying that these decomposes into water and
CO2.
CO2 gas. And what's the other product for this?
Potassium bromide, KB.
Yeah, KBr. All right, so this is the classic gas formation reaction. The classic gas formation reaction is the formation of carbonic acid, which instantly decomposes into water and CO2. So the observation for this is it's going to form bubbles. Forming bubbles, we don't call, what do we call that? We don't call it, we usually don't call it forming bubbles. We call it
Gas formation?
gas formation. We don't really call it gas formation either. We call it,
That's what I'm
starts with an E, effervescence. And so this is going to effervesce.
How do you spell that?
How do you spell it?
Effervescence, yeah.
EFFERVESCE and CE,
Yeah, that makes sense.
something like that. Well, anyway, is this balanced?
No.
No. So this is our driving force, is gas formation.
Oh.
Our other driving force would be stronger acid to weaker acid.
So does that still count when it spontaneously decomposes?
Does it still count when the carbonic acid decomposes? The answer is yes. Did you know there are different kinds of acids? The acids that we've dealt with begin with what element? H. But there's another class of acids called Lewis acids. And Lewis acid, CO2 is a Lewis acid. The acid chart I gave you on the screen there are what we call Bronsted acids. All Bronsted acids begin with H. And so CO2 is actually an acid. And so it is. Carbonic acid.
So would the strong acid to weak acid be specifically
Stronger. This is a strong acid, but it doesn't have to be strong. It just has to be stronger.
But so like for testing purposes, we would really only know like the 7 main strong acids to be
No,
strong.
for testing purposes, you have the chart.
Oh.
You don't have to memorize any of these. The only reason you memorize stronger acid to weaker acid is sometimes you don't have the chart and you have to predict in net ionic equations what breaks apart.
So it's like top to bottom, left to right.
Top to bottom, on the right side are the bases. It's a conjugate relationship.
Oh.
Yeah. So if you have a strong acid, you have a very weak base, conjugate base.
So it's kind of like the oxide.
Right, exactly, it's the same thing. Did you guys get the net ionic equation for this?
I forgot about the spontaneous decomposition, so no.
So I wanted to point this out here because we're going to write each equation with water and CO2, not carbonic acid. So starting with equation A, should have it, and B, and C. The CE, the IE, and the NIE. That's our ABC.
I don't remember. He said it like at the beginning, because he probably thought that we could do it on our own.
the one that doesn't, like, don't change, like, state? Like, that doesn't change.
We're saying like potassium.
Would you say first six minutes?
Were you guys able to get this,
Yeah, I think
the ionic equation? Okay, what did you get?
so. 2 hydrogen ions plus 2 bromine ions plus 2 potassium
Okay, tell me the charges. 2K.
plus CO3 minus. And then over to 2K minus plus, or I guess outward it's
2K minus? Like that?
wait, plus. And then plus 2BR minus. And then plus H2O and CO2.
Okay, that's good. And the NIE?
2H plus CO3 minus to H2O plus CO2.
Okay, that's good too. Did everybody get that? The first time? Were you getting stuck on something in particular, or?
Just for some reason, I was making it more difficult than it needed to be, and wasn't splitting up the potassium and the carbon. I kept it together. Yeah, I was like, unless it's aqueous, I think that's exactly.
If this were solid, then you keep it together.
Yeah.
But since it's aqueous, you
Yeah.
have to split it up.
That's exactly right. Well, because it's group 1 potassium, so that's just
Yeah,
the
group
first
1.
solubility thing.
Group 1 compounds
That's so valid.
Well, check out number 58.
I knew it.
Number 58 is the most common double replacement reaction in all of chemistry.
Gosh.
I should take note.
Yeah.
You know what the most common acid is? In the lab? Hydrochloric acid is the most common acid. Both of these are strong. Strong acid and strong base. Both of these are aqueous. Sometimes we get tired of writing aqueous. Aqueous is 4 characters, you know, parentheses, AQ, parentheses. And so oftentimes people will just omit AQ, but they'll write solid, liquid, and gas always.
So like you just leave it blank, that means.
Yeah, you can leave it blank. It gets tiring writing AQ over and over again. What did you guys form?
Water and
Yeah. This is going to form sodium chloride, just salt and water. This is a double replacement reaction, but this is also called an acid-base neutralization reaction, you know, because you take a strong acid, like hydrochloric acid, and a strong base like sodium hydroxide, you make salt water. So I remember, you know, my high school chemistry teacher used to always talk about this reaction and said, you know, you can't drink hydrochloric acid and you can't drink sodium hydroxide, but you mix them together and you can drink salt water. And so I was waiting for him to drink the salt water, you know, after mixing it, but he never did.
I mean, it's not tasty.
I don't know, if you don't neutralize all of it, you might end up with a little bit of.
Yeah, if you don't neutralize, but you know, you have to show some confidence in your chemistry skills. You know? But if you do make a mistake, you know, you do a miscalculation, it would be pretty gruesome. So I understand why he probably didn't do it. But anyway, did you get a driving force for this?
Yeah. Acids neutralizing the salt, and so the base.
Okay, but normally we think in terms of, if we're thinking acids, we're thinking in terms of stronger acid to weaker acid.
Yeah.
So the stronger acid is hydrochloric, but what's the weaker acid? Is the weaker acid the salt, or is the weaker acid the water, or both?
It has to be the water.
It has to be the water, yeah, in this case. And so actually the weaker acid is the water. Water is an interesting acid because it can also act as a base, and it's equally strong as a base as it is an acid. In other words, it's weak. I should say equally weak as an acid and equally weak as a base. A lot of things are stronger. You know, they're stronger as an acid than a base, or stronger as a base than an acid. And so they have a bias towards it. But water has no bias. It can go either way. And so a lot of people call water neutral, you know. But in this case, water is going to be our acid. So we do have driving force. Did you get the ionic equation for this? What did you get for ionic equation?
Na plus plus OH minus plus H plus plus Cl minus gets you Na plus Cl minus plus water.
Yeah, good. And water will write liquid here. And so this just saved us a whole lot of AQs. If we had to write AQ for each of these, it's kind of cumbersome. And what did you get as the NIE, the net ionic equation?
OH minus plus H plus yields H2O.
Yeah. H2O liquid. And so this is the classic acid-base neutralization. Here's our base, hydroxide, here's our acid H plus. So, yeah, but this is a double replacement reaction here. Let me ask you this. Number 59, this is an acid that you don't have on the list. This is called benzoic acid. You don't have to memorize this. But how many acidic hydrogens are there in benzoic acid? Yeah, there's just one. And so it's the first one here. These 5 are not acidic here. And so they write these behind. And so whenever we have a non-acidic hydrogen, those don't go to the front. The acidic hydrogens go to the front. And so this is just a monoprotic acid. And so this would be similar to like HCl or whatever. And this consists of one hydrogen ion and one benzoate ion. What's the charge on benzoate? Well, I'll tell you the formula for benzoate. So if we lose the hydrogen ion, we're left with C7H5O2, and the charge is
Minus?
-1 because we just have one H plus there to balance it. And so typically, this is neutralized with hydroxide solution. Did that get cut off? Let's see if that got cut off.
Sodium hydroxide.
Sodium hydroxide. So what we're going to form is sodium benzoate and hydrogen hydroxide. Sodium benzoate would just be NaC7H5O2. You know, it's just sodium ions and benzoate ions. And hydrogen hydroxide is just water. So it's similar to this, you know, except rather than having chloride, we have benzoate, and benzoate has a big formula to it. But it's pretty much the same reaction, except benzoic acid is not strong. Benzoic acid is weak. Do we dissociate weak acids? No. And so the other major difference is that hydrochloric we dissociate into the ions, benzoic we just leave alone. And so benzoic acid will make it all the way to the NIE. All right, we'll look at some more, but we're out of time now, so we'll look at some more next time.